A half-kilometer asteroid can change its own fate just by turning in sunlight, and that shifts whether it ever hits Earth. In 2023, NASA's OSIRIS-REx brought back samples from asteroid Bennu, but the mission also nailed Bennu's orbit with unsettling accuracy. Bennu is about 500 meters wide, a loose rubble pile, and it circles the Sun roughly every 14 months. When we project its path using gravity alone, it doesn't quite line up. Its semi-major axis, the average size of its orbit, is shrinking by a few hundred meters each year. That sounds harmless until you hear the calendar. Bennu passes Earth in 2135 at roughly moon distance, and after that close encounter, the forecast includes small impact probabilities later, with a modest peak around 2182. So what's providing the shove, out in a near-perfect vacuum? Sunlight sounds soft, but it carries momentum. Photons deliver tiny kicks when they're absorbed or reflected, creating a real force called radiation pressure. Near Earth, that pressure is only about 9 millionths of a newton per square meter. Yet, across Bennu's roughly 200,000 square meters of sunlit face, it adds up to around 2 newtons, half a weight. Spread over 70 billion kilograms, that changes Bennu's speed by about a millimeter per second per year. A millimeter per second is nothing to your body, but it literally changes where Bennu is along its orbit on a given date. And at a close flyby, arriving a few minutes early or late means Earth's gravity bends you onto a different outgoing path. The weird part is that Bennu's main drift isn't from reflected light. It's from heat that leaves late. The real steering comes from Bennu's own glow. Bennu absorbs sunlight, warms up, and later cools by radiating infrared, the kind of light you feel as heat. Those escaping infrared photons carry momentum too, so Bennu recoils in the opposite direction. If its surface temperature responded instantly, the emission would be symmetric and the recoil would cancel. It doesn't. Bennu spins once every about 4.5 hours, and rock has thermal inertia, resistance to changing temperature, so the hottest point is in the afternoon after local noon. Here's what physically happens. The afternoon hemisphere emits a little more infrared than the morning hemisphere. Because Bennu is also moving along its orbit, that off-center glow points slightly ahead of, or behind, the direction of travel. The recoil, therefore, has a tiny along-track component that steadily speeds Bennu up or slows it down. That changes the semi-major axis over time. This is the Yarkovsky effect. For Bennu, we measure an inward drift of about 280 meters per year, around a meter per day, because its spin is retrograde, opposite its orbital motion. No engines, just warm rock leaking momentum. Frame shift, gravity draws the loop, but sunlight edits the timing. The asteroid becomes a slow heat engine, and its spin chooses the drift direction. Not because space is windy, because every photon leaving carries momentum away. What decides whether that edit is huge or negligible? Size, tilt, and surface. Heat only penetrates centimeters, so a 10-kilometer asteroid has too much mass for its warm skin to steer it. A pebble heats and cools so fast that morning and afternoon look almost identical, and the recoil averages out. The strongest Yarkovsky drift hits bodies from a few tens of meters up to about a kilometer, exactly the size range of many near-Earth asteroids. Then comes the material itself. Dusty regolith cools quickly. Solid boulders hold heat longer, shifting the hot spot and changing the force. OSIRIS-REx saw Bennu as unusually boulder-strewn, which feeds straight into the drift prediction. Finally, there's obliquity, the spin axis tilt. It controls whether the day-night cycle or a seasonal lag over the asteroid's year dominates, and it can even flip the sign. Stepping back, orbit prediction turns into materials science. Can we actually detect a meter-per-day drift from millions of kilometers away? And does it really change the impact odds? Yes, because we don't just see Bennu, we range to it. Radar echoes time the distance to tens of meters, and OSIRIS-REx's tracking pinned down Bennu's mass and shape, so we know how strongly a given photon push can accelerate it. When you include Yarkovsky, the orbit fits. When you ignore it, the predictions walk away year after year. All that uncertainty gets squeezed into one moment. The 2135 flyby, about 300,000 kilometers away. During a close pass, Earth's gravity can scatter Bennu onto many later trajectories, including gravitational keyholes, corridors only a few hundred meters wide, that set up resonant returns and possible impacts. A Yarkovsky-driven timing shift of minutes can decide whether Bennu threads one. Today's best estimates put the peak risk around 2182 at roughly 1 chance in a few thousand. Sunlight nudges Bennu because its delayed heat glow acts like a constant micro-thruster. Infrared photons stream off the hotter afternoon side in a slightly preferred direction. Bennu recoils with an equal and opposite momentum, changing its orbit one whisper at a time. Change the surface decades early, make it brighter, darker, rougher, and you can change that drift by tens of meters per year and accumulate kilometer-scale misses. Like, if this was interesting, hit the subscribe for more and turn that notification bell on.